Series circuits, everything's sweet. Add more resistors, get more resistance. Parallel circuits, add more resistors, get less resistance. Doesn't quite make sense, which is why I get my students to think about this formula in terms of currents through the circuit rather than in terms of resistance. So let's start off by labeling the current through the circuit and the currents through the individual components. We'll call the total circuit current IT and the currents through the individual resistors I1, I2, I3 respectively. It would be expected according to Kirchhoff's current law that IT is simply just the sum of I1, I2 and I3. And you'll see this is the key to understanding the parallel resistance formula. So we have a voltage source of voltage V, and we assume there's no voltage drop in the wire itself. So every single point at the top of the circuit is at a potential of plus V. Likewise, every point down the bottom of the circuit is at a potential of 0. So by using Ohm's law, we know that current is voltage divided by resistance. So we'll change Kirchhoff's current law in terms of voltage and resistance. And the key thing now is to see that V1, V2, and V3 are the same V, and that V is the potential of the power supply. So therefore, all of the V's in the equation are actually the exact same V. So seeing as V is common to both sides, we just get rid of it. It's a common factor. And that's how we end up with our parallel resistance formula. So rather than saying adding more resistors gives less resistance, we just say adding more resistors gives more current. And then as a result, the resistance must go down as the voltage source is constant. Easy peasy. Got you an extra mark.